Let's look at this function. F of x. Let's look at a different pen. F of x equal to x to the fifth minus 5x to the fourth. And yeah, these examples might be somewhat easy to start just because I want to make sure everybody sees a couple things. Specifically, the second derivative test is what I kind of want to talk about. Let me change my settings here because there's definitely way too much light on the screen there. Hopefully you guys can see that a little bit better now. Let me feel like I should close my window a bit too. Hopefully you guys can see the board all right there. Okay, so I want to graph this thing. So when I say graph a function, I mean find all the things. Intercepts, so all the things if they exist. Intercepts, asymptotes, first derivative stuff, meaning relative extrema, also where it's increasing, decreasing, and second derivative stuff, meaning inflection points, and also where it's concave up, concave down. So I'm going to do all that for this. So first I'm going to find the intercepts. So I'm going to set x equal to 0 to find the y-intercept. I think my blue pens are kind of not the best. So we'll do some green pens. So set x equal to 0. F of 0 is going to be 0. X-intercept, we set y equal to 0. So x to the fifth minus 5x to the fourth equals 0. Factor of x to the fourth. So you've got x equal to 0 and x equal to 5. So we're just going through the usual steps of graphing a function. This is a polynomial, so we know it's not going to have any asymptotes, neither vertical nor horizontal nor slant. We could talk about end behavior. You don't really have to, though, if you know how the first derivative stuff works. So let's go ahead and move on to the first derivative stuff. When I say the first derivative stuff, I mean we're going to find the critical values. We're going to put them on the number line to see where the function is increasing or decreasing, and we're also going to use that to determine if we have any relative extrema. So let's find the first derivative. First derivative is, let's see, 5x to the fourth minus the derivative of this is 20x cubed. And we're going to see whether that's 0 or undefined. We know it's not undefined, but we're still going to say that because it's how you should think about critical values. And I really should emphasize here, when I say critical values, here I mean the critical values for the first derivative, because when I find where the derivative is equal to 0, it's that derivative's critical values. And if I find the second derivative is equal to 0, those are the second derivative critical values. At least that's what I call them. Maybe not everyone calls them that. In any event, I'm going to factor. I'm going to factor out 5x cubed times x minus 4 equal to 0. So I end up with critical values, x equal to 0 and x equal to 4. So 0, 4. I'm going to see what the first derivative is doing. So I like to write f prime over here to remind myself that I'm looking at what's going on with this, not with this. And I plug in 0. Sorry, I don't plug in 0. I plug in points that are not those points. So I plug in something like 6. 6 cubed is positive, 6 minus 4 is positive. I only care about the sign. I don't really care what the number is. So the whole thing is positive there. So that means my function f is increasing. Similarly, if I plug in something between 0, so I do this a different way usually, right? 4 came from this factor has an odd power, so the sign changes. 0 came from this factor has an odd power, so the sign changes. Or you can pick points. You can plug in 2, positive, negative, plug in -1, negative, negative, so you get a positive. Either way you want to do it. So what we have is the function is increasing, decreasing, increasing. So that means we have a relative max at, is it at 0 or is it at 4?
Zero.
I didn't quite hear that, but I'm going to go ahead and say it's at 0. And we know it's at 0 because it's increasing, right, getting bigger, and then decreasing, getting smaller. So if you go from increasing to decreasing, right, so I should say, a lot of you asked me about using the derivative to talk about the shape of the graph. This is how I do that. This here is telling me, oh, the graph is going up. I get to some point when x is 0, then the graph is going down. I get to some point when x is 4, then the graph is going up. So I now have a relative maximum at x equal to 0. I'm also going to find the y value to go with x. I'm going to have to graph it, but I already know that because I already found that when I found the y-intercept. So really, this is at the point 0, 0. And at 4, I have a relative minimum, right? The function was going down and then got to 4 and then it was going up. So I have a relative minimum at x equal to 4. Or if I want to actually find the y-coordinate, now this one's going to be kind of gross because the numbers are kind of big. I could plug into this, but I'd rather plug it into this because it's a little bit easier to plug it into when it's factored. So I'm going to get 4 to the 4th times 4 minus 5. So it's 4 to the 4th times negative 1, so that's a negative 4 to the 4th. 4 to the 4th is 256. So that's going to be 4 comma negative 256. We won't worry about the y values being to scale. So I already know what my graph really looks like. Even without doing the second derivative stuff, I have a pretty good idea that my graph is going to do the following. Here's 0, 0. Here's, 4, so 1, 2, 3, 4, 5. So here's 0, 0. Here's 5, 0, which is also next intercept. And then 4, negative 256, which is somewhere down here. So I know I'm going to be increasing before I get to 0, decreasing afterwards. And then after I get to this point here, 4 comma negative 256, it's going to be increasing after that. Right? So the first derivative really does help me with the shape of the graph. The second derivative is more for, really it's mostly for finding inflection points. It also does help us though kind of make sure our graph is the right shape because it also talks about concavity. And concavity, well, there's a couple ways of describing concavity. I generally think of it as the way the graph is opening. So this part to me looks like it's concave down because it's opening down. This part over here appears to be concave up. I will also mention, some people like to think about it like a car. If you think of this as like a map, like a road map, the graph is the road and the car is driving this way. If the car is turning to the right, you're concave down. And then at some point here, you switch and you start turning to the left, and then it's concave up. It's another way you can think about concavity. Let's go ahead and find where concavity is up and down. So I'm going to take the second derivative. I don't want to take the derivative of this. I'd rather not use the product rule. I'm going to take the derivative of this version of it instead. So f prime is 5x to the 4th minus 20x cubed. This kind of might be garbage. It's time to call the pens. So my second derivative here is going to be that, so 20x cubed minus 60x squared. Factor out the 20x squared, I'm left with x minus 3. So I end up getting x equal to 0 as a critical value for the second derivative, and x equal to 3. So using this number line for my second derivative here, 0 and 3. If you get a number larger than 3, like 4, positive, positive, that means the function is concave up. In between 0 and 3, like 1, positive, negative. So it's negative overall, which means it's going to be concave down. And if we get a number like negative 1, negative, positive, negative, so it's going to be concave down again. Okay, so this tells us a couple things. First of all, it tells us our graph is looking good, right? It's concave down to 0, concave down to 3, and then concave up after 3. So somewhere over here at like 3 comma whatever, we have an inflection point where the concavity changes from concave down to concave up. So an inflection point at x equal to 3. Or if you prefer, and I do prefer, and you usually do want to find the y values, 3 comma whatever you get when you plug in 3 to the original function. So 3 comma f of 3, which would be 3 comma. So if I go, let me start my function here. So f of x was x to the 5th minus 5x to the 4th, which is x to the 4th times x minus 5. If you plug in a 3 there, 3 to the 4th is 81. 3 minus 5 is negative 2. 81 times negative 2 is negative 162. Again, I know the numbers here are not really particularly beautiful. That's how it is sometimes. So this point here, not that my graph is to scale, is the point 3, negative 162. Okay, so that is a full graphing of this function. But there is something I didn't talk about yet in this particular example, and that's the second derivative test. So we use the second derivative here to find the concavity. I suppose I could do a little bit more. So if you were asked, we could also say that this function, so the intervals of increasing or decreasing, so this function is increasing on the interval from negative infinity to 0 and 4 to infinity. It is decreasing on the interval from 0 to 4. And then similarly, if we want to talk about concavity, you can say that this function is concave up on the interval from 3 to infinity. And it's concave down on the interval from negative infinity to 3. And we would include this 0 because it's concave down here, it's concave down here. And since the function is defined at the point between those two intervals, we include it. Negative infinity to 3. Okay, but that still doesn't actually have anything to do with the second derivative test. So the first derivative test for relative extrema is just what we did here. We found the critical values from the first derivative, and we determined if they were relative extrema by seeing if it was increasing, decreasing, oh, we have a max, or if it was decreasing, increasing, oh, we have a min. Right? So for a critical value from the first derivative, if the function goes from increasing on the left of it to decreasing on the right of it, we have a relative maximum. If for a critical value, the function goes from decreasing on the left of it to increasing on the right of it, you have a relative minimum. And if it's something else like decreasing, decreasing, or increasing, increasing, you don't have a relative extrema there. There is something else, though, called the second derivative test for the first derivative relative extrema. I mean, they just say it's for relative extrema, but yeah. So here's how that works. Again, I don't particularly recommend this, but occasionally it is nice. So here's the second derivative test for relative extrema. Again, I don't typically use this unless someone forces me to, or occasionally with an optimization problem. But here's what you can do. You can take your critical values, 0 and 4, and you can plug them into the second derivative. So again, remember our second derivative, I'm going to give you the factored form. Our second derivative is 20x squared times x minus 3. And then I'm going to plug in 4. F double prime of 4 is 20 times 4 squared times 4 minus 3. And honestly, I don't care what it's actually equal to. I just care whether it's positive or negative. In this case, I've got 20 times 16 times 1. That's going to be positive. It's going to be 320. It's positive. Okay, so let me ask you guys. If the second derivative is positive, what does that mean about the shape of the graph? Is it concave up or is it concave down?
Concave up.
Right. So if your function is concave up and your point is either a relative maximum or a relative minimum, what's it have to be?
A minimum.
Right. Which is exactly what the graph is showing us. If you look at this point here, oh yeah, right there at 4, it is concave up. So, and oh yeah, that's definitely a minimum of 4. Now here's the failing of the second derivative test. If the second derivative is 0, that alone won't tell you whether it's a max, a min, or neither. And if I plug in 0 here, definitely when I plug in 0, I do get 0. So this doesn't tell me anything. We know from the work we already did that 0 happens to be a relative maximum. However, you can have the second derivative equal 0 and have something that isn't a relative max. It could be a relative minimum, or it could be neither. So the second derivative test, if it's equal to 0 at your critical value from the first derivative, it's inconclusive. So that's what you should know about the second derivative test. Yeah, you can plug in your first derivative critical values to the second derivative. And if it's positive, you've got a relative minimum because it's concave up. If it's negative, you've got a relative maximum because it's concave down. And if it's 0, we don't know anything. In this case, when it's 0, we happen to have a relative maximum. However, let's look at another example. Another easy example, and then we'll do some harder graphing examples. And there's a couple people sent me a couple different problems that seem They're worth checking out. So let us look at, now let's do this other. This is kind of my other standard easy one. I mean, relatively easy. It still works. So let's look at g of x equal to x to the fourth minus 4x cubed. You might have noticed a pattern. I've got like a power of x minus its derivative. They work out nicely. Let's make it plus. Let's make it, sure. I'll make it a little more exciting. Why not? So let's find all the things. So first, intercepts. Y-intercept. Set x equal to 0. You're going to get g of 0 is 0. How exciting. X-intercepts. Set the whole thing equal to 0 and factor. Let's see what the heat's at. It feels a little warm here. Yeah, it's a little too hot in here. Okay, so factor on x cubed times x plus 4 equal to 0. So we get x equal to 0, we get x equal to negative 4. All right. So before I start graphing all this stuff, let's find the first derivative stuff. Right, because again, there's no asymptotes. It's a polynomial. You never have asymptotes when there's a polynomial. Let's find the first derivative. So the first derivative here is going to be 4x cubed plus 12x squared. And that's going to be a factor out of 4x squared. I'm left with x plus 3. And so I end up getting x equal to 0 and x equal to negative 3 as my critical values. Now, let's go ahead and actually use the second derivative test before we do the first derivative test, just so we can really see that, oh yeah, sometimes the second derivative test doesn't tell us enough. So let's find the second derivative. Let's do it over here. The second derivative is, let's see, 12x squared plus 24x. And I think it's always a good idea to factor these, especially if you're going to be plugging stuff into them. So that's equal to 12x times x plus 2. All right, so now I'm going to plug in negative 3 and see what happens. So g double prime of negative 3. If I plug in negative 3, I get negative 36 times negative 1. 12 times negative 3 times negative 3 plus 2. That's negative 36 times negative 1, which is positive 36. So here's what we know. We know that since g double prime of negative 3 is a positive number, that the function is concave up at that point. But that point is a potential relative extrema. And since the function happens to be concave up at it, we know that it is a relative minimum. So we definitely have a relative minimum, or local, you can say local minimum. I just usually say relative, I don't know why. Relative minimum at x equal to negative 3. This will also be borne out when we do the first derivative test with the sign chart. But I just wanted to show you guys that the next part isn't so great. We do g double prime of the other critical value, which is 0. You end up getting 0, right? 4 times 0 times 3. And this means we don't know. It could be a relative max. It could be a relative, right? It could be a relative maximum. It could be a relative, yeah, like it was, right? It could be a relative maximum like it was before, right here. The second derivative was 0, and we had a relative maximum. So it could be a relative maximum. That's certainly a possibility. It could be a relative minimum, or it could be neither. And the thing is, this isn't enough information. We have to use the first derivative test with the sign chart to actually know when you have an inconclusive one like this. Also, the first derivative sign chart is great for showing us the shape of the graph, so we should do that anyway. But I wanted to tell you, right, if you do the second derivative test, sometimes you're like, I don't know. So the first derivative, sorry, was there a question there?
Yeah, I had a question.
Go ahead.
So if the second derivative equals 0, would you consider the g double prime of 0 to be an inflection point?
No. Right? So that's a really good question, though. And the answer is really genuinely we have to do more work. In this problem, it wasn't, right? We had a place where the second derivative was 0, but we ended up having a relative maximum there. I will tell you that this other example, we are going to have an inflection point there, but I want to say generally, we don't know. We have to do more work. You have to use these shine charts to really find things. So this is why I will say, I don't usually recommend using the second derivative test for anything. I mean, that's not entirely true, but if you're graphing, you really don't need the second derivative test. You're going to use the first derivative sign chart to tell you if you have any relative maxes or mins, and you're going to use the second derivative sign chart to tell you if you have an inflection point. But I should say even more specifically to answer your question, the second derivative being 0 is never enough to definitively say you have an inflection point. To definitively say you have an inflection point, you have to see that the concavity is changing signs on the left and right of whatever your possible inflection point is. But very good question. Thank you.
Thank you so much.
And thank you so much. Anyway, so going back to my first derivative here. So I'm going to put -3 and 0 on my sign chart in the correct order. And obviously so here's the thing, we know that -3 is going to be a relative minimum. So we already know in our minds that, oh, it should be decreasing and then increasing so that it can have a minimum. But let's actually check. So I pick something less than -3, like -4, and plug it in here. That's a positive times a negative, so it's going to be negative. And I pick something between -3 and 0, like -1, that's a positive times a positive. And then if I pick something bigger than 0, it's a positive times a positive. So my function is decreasing, increasing, increasing. So we don't have a relative extrema at 0. It's not a relative maximum, it's not a relative minimum. The function is increasing, and then it's increasing after that. Which means we probably do have an inflection point at 0. Right? Typically, if you've got something that's a critical value for the first and the second derivative, right here 0 is the critical value for the first derivative, it's also a critical value for the second derivative. Usually it's going to be either a relative extrema or an inflection point. So if it's not a relative extrema, it's probably an inflection point. Well, let's do the work just to double check. Right? Probably is not enough to say for sure. So here's our second derivative, 12x times x plus 2. And the critical values for my second derivative are, in addition to x equals 0, also x equal to -2, right? Because those are the things that make that equal to 0. So on my second derivative sign chart, I'm going to put 0 and -2. And then I'm going to look at the signs of the second derivative in between each of those intervals. So if I pick a number larger than 0, like 5, 12 times 5 is positive, 5 plus 2 is positive, it's positive. And then you can see that 0 comes from x to the first, so the sign's going to change. -2 comes from x plus 2 to the first, so the sign's going to change. Or you can pick points, right? You can pick -1, 12 times -1 is negative, negative plus 2 is positive, product is negative. Pick -3, negative, 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 negative is positive. The function is concave up, concave down, concave up. So let me ask you guys, do we have an inflection point at 0?
Yes.
Yes, because the concavity changed. Do we have an inflection point at -2?
Yes.
Yes, because the concavity changed. So yes, we have inflection points both at 0, 0, right? Because when you plug in 0, you get out 0. We already know that's a point in the graph. And also at -2, comma, f of -2. That's what kind of I do first when I'm lazy, or I'm like, I know there's a y value there. I should say, oh, there's a y value there. But then I should actually figure out what it is. So my function was, again, x to the 4th plus 4x cubed. So, right, g of x was x to the 4th plus 4x cubed. You could plug in -2 here. It's not too terrible. But instead I'm going to factor, sorry, I couldn't help myself. I'm going to factor out an x cubed, and then plugging in -2 is going to give me a -8 times a -2 plus 4, which is a +2. So -8 times 2 is -16. So g of -2 is -16. So those are my inflection points. Now I can graph the thing. I mean, I could have graphed the thing before, but I've got 1, 2, 3, 4. I've got an x-intercept at -4. I've got a relative minimum at -3. Oh, I didn't find the y value. I should have done that. So if I plug in g of -3, I get, let's see, so if we can factor out an x cubed, it's -3 cubed times -3 plus 1. Sorry, -3 plus 4, which is 1. So that's going to give me -27 times 1, which is -27. So that's my relative minimum. So I got -3, -27, which is somewhere down here. I've got my inflection point at -2, -16, so maybe somewhere about like there. And then I need my sign chart. So I'm decreasing until I get to -3, increasing after, and then increasing after. So watch this. So I'm, decreasing. And then, so I stop being concave up, I start being concave down. And then right at 0, I have to flatten out because 1, the derivative is 0 there. And 2, I have to change concavity from being concave down between -2 and 0 to concave up, like that. So there's our graph. Concave up, concave down, concave up, relative minimum. That's kind of it. And then you could write the intervals where it's increasing or decreasing, or concave up, right? It's concave up from -infinity to -2, union 0 to infinity. It's concave down from -2 to 0. And then it is increasing from -3 to infinity, right? Because it's definitely increasing here, and 0 is included because the function is defined as 0. And it's definitely decreasing from -infinity to -3. Okay, well, there's my blue pen. I'm gonna only got like 5 of them. Okay, let's look at a couple more examples that are less nice. Can we go over an example of a closed interval? Like finding absolute extrema? Is that what you're talking about, Michaela? Yes, okay. Yeah. So in fact, we could, so let's piggyback on this example. So let's say for this example, I wanted to find, sorry, go away here. So let's say this example was given, but instead of the question as is, we were told to, let me see, I want to keep some important information here. That's exactly, no, that'd be fine. So let's say we were given this problem. We were asked to find the absolute or global extrema for this function on the interval from -5 to -1. So the process for this starts off the same in that it starts off by finding the derivative and finding the critical values. So the critical values are definitely x equals 0 and x equals -3. So then the only thing we do at this point is we plug those all into the original function. So I'm going to find, and I'm going to definitely factor the original function to make my life easier. But you should factor it right. I factored it wrong, right? It's not x cubed times x plus 3, it's x cubed times x plus 4. So plugging in, so let's see, I'm going to find g of 0, g of -3, g of -5, and g of -1. Right, so you're plugging in the critical values and the endpoints. Now, I have made a tiny mistake, but I'm wondering if anyone knows what the mistake is that I've made. It's okay if you don't. I'll tell you guys.
0 isn't in the domain.
Yeah. So oftentimes one of your critical values, or maybe more of them, won't actually be in the interval you're looking at, and so you shouldn't consider those. And let me go on like I'm gonna pretend like I'm still making the mistake, and we'll see why it's really kind of important not to make that mistake. So, except it's not going to actually matter here anyway. So anyway, if I plug in 0, I would get 0. I plug in negative 3, I get negative 27 times 1, which is negative 27. I plug in negative 5, I'm going to get negative 125, right? Negative 5 cubes, negative 125, times negative 5 plus 4 is negative 1, so I'm going to get positive 125. And then finally, g of negative 1 is going to be negative 1 times 3, which is negative 3. So our job here is to pick which one is the biggest and which one's the smallest. And the problem is, right, if we included this one, I mean, it's not a problem here, actually, in that it's still a problem to consider, right? That's wrong to do. But it's not a problem because it actually doesn't end up being the biggest or the smallest. So in this particular case, our biggest value is 125. Our smallest value is negative 27. So we can say that we have an absolute maximum. So this is where you have to be careful. What's your language? Have an absolute maximum value of 125 at x equal to negative 5. Have an absolute minimum value of negative 27 at x equal to negative 3. So if they're asking you for the maximum or minimum value, they want the y part. If they're asking you where the absolute maximum or minimum occurs, they want the x part. So let's do a couple more graphing things. I should also point out, right, these graphing problems are certainly kind of setting us up to think about optimization, because the process for optimization is you're trying to find where you have a maximum. Well, we know how to find a maximum, right? We've just been doing graphing problems where you, well, not this one, but the previous one where you find your relative maximum. That's kind of how we do that. But I have a couple more graphing problems I want to show you guys. In fact, let me sorry, give me 1 second here. I feel like my wife is talking to me very loudly. Not you. Sorry, I'm just. Okay, yeah, there's all these weird. There's some. We'll definitely get to some optimization here in a minute. You guys have. There's some weird optimization problems that I'm seeing here. Yeah, but let's go ahead and I want to do one or two more graphing problems, and then we will do some optimization. So where'd you go? Sorry, I typed this one out. Someone sent me this one. So let's say we have, So let's say we have the function f of x equal to x squared over x squared. I'm going to go with minus 4, even though the one I was sent was plus 4. Minus 4 is a little more interesting. And I want to find, I really just want to find the relative extrema, but I'm going to do all the things. So let's find intercepts. So x-intercepts at y-intercept. X equal to 0, you're going to get y equal to 0. X-intercept set y equal to 0, or the function equal to 0. And you're going to get x equal to 0. So then we also have to consider asymptotes here. So for the asymptotes, I'm going to get a vertical asymptote when the denominator is 0. So x squared minus 4 equals 0. So solving that, I'm going to get x equal to plus or minus 2. So I'm a vertical asymptote at 2 and at negative 2. And then for horizontal asymptotes, I see that it's a rational function where the degree on the top and the degree on the bottom are the same. So we have a horizontal asymptote at the quotient of their coefficients, which is 1 over 1. So the horizontal asymptote is y equal to 1. All right. The first derivative and second derivative stuff gets kind of messy for these rational functions here. So let's take a quick look. F prime of x is going to be, so it's the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So simplifying this, we get, let's see, x squared times 2x is 2x cubed. 2x times negative 4 is negative 8x minus 2x cubed, all over x squared minus 4 squared. The 2x cubes cancel, so we get negative 8x over x squared minus 4 squared. Now, something I have seen with this particular type of problem is that it does kind of pay to actually maybe factor the denominator. So the denominator is actually, x squared minus 4 is x minus 2 times x plus 2. And it's that quantity squared. So I've really got negative 8x over x minus 2 squared times x plus 2 squared. Okay. So let me write this on the other side of the board. But I want to ask you guys what my critical values are. You go ahead and type them in the chat. Nobody's typing them in the chat? How disappointing. 0. So I will have to say that technically Stephanie is correct and fully correct, meaning technically 0 is the only critical value here. So my critical values are x equal to 0. However, 2 and negative 2, although not technically critical values, are still important to include to see how the graph actually looks. But we know they're not actually critical values because they're not in the domain of the original function. There's vertical asymptotes there. If you have a vertical asymptote somewhere, we know we actually can't have anything else there, right? There can't be a relative max, there can't be a relative min. So just be careful. When you have critical values like this, they're not really critical values, but we still want them on our sign chart. Take our first derivative sign chart. So I know that I've got 0 and 2 and negative 2. And I'm just going to look at what's happening. So if we get a number larger than 2, like 3, negative on top, it's definitely positive on the bottom because the bottom, both things are squared, so the bottom's always positive. So it really just depends on the top. So it can be negative overall, and then pick something between 0 and 2, top's negative, bottom's always positive. Pick something between 0 and negative 2, top's positive, bottom's always positive. Pick something less than negative 2. Top's positive, bottom's always positive. The function is increasing, increasing, decreasing, decreasing. I know, so, and actually I just started doing this because I was talking to someone else and I was like, oh, this is a good idea. I like to make open circles at this point. So like, oh, it's undefined there. You can even like draw yourself a little vertical asymptote. You're like, oh yeah, I can't have anything else happening there. And then, but at 0, we do know we have a relative what? Relative maximum or relative minimum at x equals 0? Yeah, definitely a relative maximum. Now, I don't really want to find the second derivative here because it's kind of a pain in the butt. So I don't know how many of you guys are aware of this, but I feel like everybody should know about the Wolfram differentiator and also integrator for next quarter. So let me just show you that real quick because it seems like it's worth having seen at least once. So literally, I'm going to Google Wolfram differentiator. Differentiator. Can I spell? Maybe. Close enough. Good. Okay, so here's the derivative calculator. Awesome. And I mean, there's lots of these. This is just the one I've always used. So I'm going to throw that equation. Actually, I'm going to write it more simply. I'm going to write this one in there. So it's negative 8x divided by x squared minus 4 quantity squared. Awesome. Let's see what we get. Takes a minute. I mean, less than a minute. It takes a few seconds. So you get, right, let's see, it actually is what I wanted, right? It's negative 8 times x over x squared minus 4 squared. Then they give you like all the stuff. They give you the graph of it, they give you the forms, partial fractions, and somewhere down here, there should actually be the derivative. So there's my derivative. It looks really gross. I didn't want to spend the time calculating that. I did want it so I could finish my graph. So the second derivative here, f double prime of x, is indeed 8 times 3x squared plus 4 over x squared minus 4 cubed. And I might rewrite that, so I'm going to stop sharing. Sorry, one sec. So I might rewrite that like I kind of did here, where instead of x squared minus 4 to a power, it's really x minus 2 to that power times x plus 2 to that power. This is going to be 3 times x squared plus 4. Sorry. It's going to be 8 times 3x squared plus 4 over x minus 2 times x plus 2, all to the third power, but I'm just going to write that as x minus 2 cubed times x plus 2 cubed. All right, what are my critical values here? Oh, thank you, Jack. You're definitely right. 2 of them are 2 and negative 2. I'm kidding. I mean, I'm not kidding, but, right. Basically, once something's a vertical asymptote in the original function, it's always going to be on your list of critical values, even if it's not technically a critical value. And in this particular part, these are the only critical values. This function is never equal to 0 because this numerator is something x squared plus 4, meaning it's always greater than or equal to 4. It's actually always greater than or equal to 32 because it's 8 times that, but it's never going to be 0. So these are our only critical values. So let's talk about concavity. So pick a number larger than 2, like 3. The top's always positive. 3 minus 2 is positive. 3 plus 2 is positive. The bottom's positive. Pick a number between them, like 0. The top's positive. 0 minus 2 to the third is negative. 0 plus 2 to the third is positive. So it's going to be negative here. And then finally, pick a number less than negative 2, like negative 3. Top's still positive. Negative 3 minus 2 is negative. Cubed is still negative. Negative 3 plus 2 is negative. Cubed is still negative. Negative times negative is positive. So it's concave up, concave down, concave up. So I definitely have an inflection point at 2, right? You guys are like obviously staring at us for a reason. No, of course you don't have a negative inflection point at 2, right? We already know we have vertical asymptotes at 2 and negative 2. So even though the concavity is changing at negative 2 and 2, we can't have an inflection point there because we don't have any point there. We have a vertical asymptote.
I had a really quick question.
Yeah, go ahead.
So when you get the signs on the bottom right with the concavity things, you got the positives and negatives from plugging in the negative 2 and positive 2?
No, I'm never plugging in the actual critical values. I'm plugging in the value, something to the over here. So I picked the number 3. I plugged in 3 to the top, it's positive. I plugged in 3 to the bottom, it's positive, positive. And then between them, I plugged in 0. Plugged in 0 to the top, it's positive. 0 on the bottom, negative 0 minus 2 is negative, and negative cubed is still negative. 0 plus 2 is positive, but positive cubed is still positive. So this is a positive over a negative times a positive, which is negative overall.
Okay, thank you.
Well, yes, but you're never actually plugging in those numbers, because if you're plugging in those numbers, in this case, it's just going to be undefined. So then for the graph. So we've got a lot of information, but not a lot of points. We've got 1 point, 0, 0. We've got a vertical asymptote at 2, negative 2, a horizontal asymptote at 1. And that's kind of, and then we've got the shape. So we've got 0, 0. Some vertical asymptotes. And a horizontal asymptote at 1. But that's kind of enough, because we know it's concave down in the middle. Oh, well, actually, I should say, we should really look at this for a second. We know it's increasing, increasing, decreasing, decreasing. So before negative 2, it's increasing. So we have to increase up to infinity, because that's the only thing you can do if you're increasing towards a vertical asymptote. And then after this, we're also increasing. So we can't come down like that because we'd be decreasing. We have to go up like this so that we're increasing. Top out our relative maximum, decreasing afterwards. And then after this vertical asymptote, we're still decreasing. And look, the concavity works. Concave up, concave down, concave up. To answer a couple more questions about this function, we would say that it's increasing on the interval from negative infinity to net. I should write it down. I'm gonna erase the second derivative here. So we would say that this function is increasing from negative infinity to negative 2, union negative 2 to 0. For this one, we have to break it up because it's not defined at negative 2, unlike our previous examples. We would say it's decreasing from 0 to 2, union 2 to infinity for the same reason. We'd say it's concave up from negative infinity to negative 2 union 2 to infinity. We say it's concave down from negative 2 to 2. All right. So let's switch gears. Go ahead, yeah.
So like what if, you know how on the bottom part you got the 2 and negative 2 because you factored the bottom, but like what if you have a number that can't be factored?
Then you don't get a critical value.
It
So,
just wouldn't be.
for example, if you have something like, if you have like x over x squared plus 9, here the denominator is never going to be 0 because it can't be 0, right? Because it's always positive. So yeah, so if you can't factor the denominator because, so I should kind of clarify. Not factoring is like, for example, if this problem was x squared minus 3 instead of x squared minus 4, well, you might say you can't factor the bottom. I said, well, yeah, you can. You can factor that as x minus the square root of 3 times x plus the square root of 3. So you can factor things. Sometimes they're just weird. On the other hand, you definitely can't factor x squared plus a number. That doesn't factor at all with real answers. Does that kind of answer your question, Carissa?
Yeah.
But the bigger answer to your question is we want to factor as much as possible because it makes it easier to see things. All right, so let's switch to an optimization gear here. There was one other graphing question about something x times e to the something negative x, but I think I want to save that one for Thursday after we've talked about L'Hopital's rule a little bit, because there is, at least if you're graphing it, there is kind of a L'Hopital's rule piece of it that we should talk about. Let me look at my list here. Oh yeah, there was that. Sure. Okay. So let's start with the optimization problems that are more like physical things, and then we'll move towards the less physical, more just functional ones. So oftentimes optimization problems, they give you some kind of setup and they say, I'm going to give you so much material to work with, build me a thing that has the most area or the most volume. Or the other kind of version of that is, I want you to build me a thing with so much volume. What's the shape that's going to use the least amount of material or area? So here's an example somebody sent me. If 1,200 square centimeters of material is available, to make a box with a square box and an open top, to construct an open top box. That's how we do an open top box with a square base. What's the question? I already know that. So the way this one's particularly phrased is find the largest volume the box can have. This is not my favorite way of asking the question. Typically, I usually prefer or find the dimensions of the box with the largest volume. But I want to point out how these questions, although very similar, are in fact different, right? In this question in red, we're going to just find what the actual volume of the biggest box is. This question in green, we're going to find the dimensions of that box and say, oh, it's a this by this by this box. Either way, we should draw a picture. So let me just turn around in circles here. So here's the picture of my open top box. Right? Great. It's a great looking box. And you could draw like the dashed lines back here if you want to. I don't really like drawing all these parts, but yeah. There's my not great looking open top box. Okay. So I want to, it's got a square base. So I should label the base as X and X. And the height is not the same as the base necessarily. It could be, but we don't know that for sure. So if you don't know things are the same, you should always give them different variable names. So we'll call that Y. You can use anything you want. I use X's and Y's, usually use L's and W's or H's, whatever. something else I want to say. Just to kind of point out, right, there are lots of different shaped boxes you could construct. You could make a box that was stupid. You can make a box. Oh, sorry. Now I'm having to think about what my examples are going to be. It's always hard when the surface area is like, I can make a box that's 10 by 10 by, that's 100 on the bottom, and then I still have 1100 left divided by 4. 1100 divided by 4 is 275. And so I can make a box that's 10 by 10 by 275. And it would have 1,200 square meters of surface area. Right? The bottom is 100 square meters, and each side is 275, and 275 times 4 is 1,100. Or you can make something that was, I don't know, bigger. You can make something that was, maybe not bigger, I don't know. You can make something that's wider. You can make something that's like 20 by 20. 20, 20, which is 400 on the bottom. Sorry. And then let's see, if it's 400 on the bottom, I've still got 800 left. So I want to have, I probably accidentally just picked the one that's the right answer. Sometimes that happens. I think I want 20 up here too, yeah. Right, so this box would also have 1,200 square meters of surface area. 400 on the bottom, 400 on each side. The volume here would be 800 cubic centimeters. The volume here would be 100. This one seems like it's I feel like my numbers might be off here somehow. It's all right. Yeah, that should be a 27.5. It's a little bit better. Okay. This one would have 10 times 10 times 27.5. So, right, there's lots of boxes we could make. You can't usually, unless you get lucky. Right, so maybe this is the biggest one. We don't know that. There could be a bigger one. We have to actually do the work. So, what are we trying to maximize here? We're trying to maximize volume. I'm going to maximize volume, and the volume of this open top box is x times y. And I think it's good to start off with the thing you were trying to optimize. What's my constraint? Well, I'm constrained by the fact that I only have 1,200 square meters of surface area to work with. So my surface area has to equal 1,200 square centimeters. I said meters, I meant centimeters. Okay, but I need an equation here, right? There's actually an equation for surface area of really any shape. This particular shape, there's 5 sides. There's the bottom, and there's the front, left, right, and back. So the surface area is actually given by the equation x squared plus, I've got an xy plus an xy plus an xy plus an xy. There's 4 of those. Here's what we're going to do after this. So we've got our thing we want to maximize, we've got our constraint. The rest of it is kind of it's very much the same kind of pattern each time, meaning I'm going to take my constraint, I'm going to solve for one of the variables. Which one is easier to solve for, x or y? Clearly y, right? There is less, right? If we're trying to solve for x here, right? So I should say, yeah, it's okay, right? If there's only one y, solving for y is going to be easiest. If there's multiple x's, solving for x's could be challenging to impossible. Here it would be possible. You have to complete the square, which we don't want to complete the square. So we're going to isolate y. So I'm going to get 4xy equal to 1,200 minus x squared, and then divide that by 4x. So y equals 1,200 minus x squared over 4x. Some people like to simplify this, right? Write it as 1,200 over 4x, which is 300 over x, minus x squared over 4x, which is x over 4. I think it's better to wait because sometimes you get some simplifying before you do that. So, meaning the reason I solve for this is now, well, I should back up a tiny bit. I'm trying to maximize this thing. Usually the way we maximize a function is by taking its derivative and setting it equal to 0 to find the critical values. The issue at hand here is that this function is a function of too many variables, or 2 variables in this case. Right, but that's too many. We want a function of 1 variable so we can differentiate and find the critical values. So the reason we're setting this constraint, the reason we're solving for one of the variables in this constraint equation so that we can take that isolated y and plug it into this thing we want to maximize so that we can have a function of 1 variable, which we can then find the critical values for. So that's why we are doing this. So our volume is x squared times y. And now we also know that y is 1200 minus x squared over 4x. And then we're going to plug this in for y right there. So volume now as a function of just x is x squared times 1200 minus x squared over 4x. And I like waiting for a second because then I can see I can cancel this x with one of these x's. So I can write this as x times 1200 over 4 is 300 minus x squared over 4. And then I can even distribute, and I should distribute if I'm going to have to take the derivative. So my volume is going to be 300x minus x cubed over 4, or 1/4 x cubed. And now we can differentiate. So let's find the critical values. Take the derivative, it's 300 minus 1/4 times 3x squared. I'm going to set that equal to 0. I'm going to solve for x. So let's see. I'm going to add this over here. 300 equals 3/4 x squared. Multiply both sides by 4/3. So I end up getting 4/3 times 300 is 400. 400 equals x squared, and then I get x equal to, technically the solutions are plus or minus 20, but in this particular problem, it doesn't make sense to think of x as being a negative value. So our only real solution, or our only sensible solution, is x equal to positive 20. All right, so now to answer the actual question that was asked. I'm asked the question in red. The question in red was, what's the largest volume? Well, to find the largest volume, I can just take x equal to 20 and plug it into my volume equation right here. So you could say, oh, okay, well, volume when x is 20 is going to be, and you can pick either one. I don't really know which one is better. I guess I'll plug it into this one. 20 times 300 minus 20 squared over 4. 20 squared is 400. 400 over 4 is 100. So I'm getting 20 times 300 minus 100, which is 200. I'm getting 20 times 200, which is 4,000. 4,000 cubic inches. On the other hand, interesting. I always have axes. Oh, interesting. Yeah, I was drawing my picture before a little bit wrong. It's all right. On the other hand, we can answer the question in green. Say, well, what are the dimensions? Well, I know that x is 20 inches. I still have to find y. Now, if you're asked for the dimensions you don't know yet, there is almost always going to be an equation for it that you've already done in your work. And usually it's the equation you got when you were isolating a variable. Y is equal to this, 1200 minus x squared over 4x. So y is equal to 1200 minus x squared over 4x, which is going to give us y equal to 1200 minus 20 squared over 4 times 20. So 80. So 1200 minus 400 is 800. 800 over 80 is 10. Because I'm not smart, Emily, that's why. Yeah, good call. Not inches, centimeters. Centimeters cubed. Good. Yeah. Because I forgot what my units were. That's really bad. Yeah. So and then x would be 20 centimeters. Y would be 10 centimeters. So you could either answer this question depending on how it's asked: is the volume is 4,000 cubic centimeters, or the dimensions are a 20 by 20 by 10 centimeter shape. And then 20 times 20 times 10 does give you 4,000. So, oh yeah, that makes sense. Something else. Let's see. Is there anything else I want to say about this particular problem? Oh, there is one other thing I want to say. So, most of your Weber problems probably won't ask you to do this. But technically, we didn't check to see if this was a maximum. We found a critical value, We said, oh, that's where our maximum is. But how do I know it's not a minimum? So the long and the short of it is, if you're asked to find a maximum, the thing you're going to find is going to give you a maximum. But you should be careful, especially on an exam. Someone could ask you to actually show that the thing you found is a maximum indeed. So to show that we actually have a maximum, we're going to use the first or the second derivative test. I would probably we can go second derivative test for sure. So this is where I actually do like the second derivative test, because if I take the second derivative here, it's not hard. Right, here's my first derivative. Okay, my second derivative is going to be the derivative of 300 is 0. Derivative of negative 1/4 times 3x squared is going to be negative 1/4 times 6x, which is negative 3/2 x. And if I plug in my critical value, which was 20, I see that v prime of 20 is going to be negative 3/2 times 20, which is negative 30, which is negative, which means it's concave down, which means I have a relative maximum. It's actually an absolute maximum because it's the only critical value. So sometimes people might ask you to actually show something is a maximum, as opposed, or I should say, to verify it's a maximum, as opposed to kind of just letting that kind of fade in the background. But again, I will say, if they're asking you to show something has a maximum, you're going to find a maximum. If they're asking you to show something has a minimum, you're going to find a minimum. No one's going to ask you to show something has a maximum and have there not be one. I should say, as far as I know, I suppose there could be a Weber question where it's like, find the maximum value of this function, or say that there isn't one, right? I guess that's something that someone could do if they were unkind. Let's look at another physical example, and then we'll do so. And then I think we can squeeze in one. Yeah. The problem with these optimization problems is they are definitely time consuming. So let's look at this one. Find the largest possible area of a right triangle whose hypotenuse is 20 centimeters long. Okay. So here's my shape. I want to find the largest possible area. So I want to maximize the area. And my bet is that you're going to get that both of these sides are the same length. But we don't know that yet. So let's call them, I don't know, base and height. Or whatever letters you want to use. So what am I trying to maximize? I'm trying to maximize area. So the thing I want to maximize area is 1/2 base times height. And again, the thing I want to maximize is, or has, too many variables, right? Base and height. Those are both variables. I only want one variable. So again, I need a constraint. So here our constraint is the fact that the hypotenuse has to be 20 centimeters. How do we get that constraint into an equation that involves base and height? What's an equation involving the three sides of a right triangle? Everybody's favorite theorem that starts with a P.
Pythagorean theorem.
Right. I mean, there's probably other theorems that start with a P, and maybe someone else is someone's favorite. But I mean, that's the one everyone knows. So then solve for either one. And in this case, it doesn't really look like it matters which one we choose to solve for. We can solve for B or for H. It's the same amount of work either way. And also looking at the thing I want to maximize, it's pretty much the same for B or H. So plugging into that one. Sometimes, like if this, if on the other hand, this was like 1/2 B times H cubed, I might solve for B because plugging into H and then cubing it might be worse. So look at both what you're solving for and what you're plugging into to make your choice as far as which one you want to solve for. But here I'm going to pick, it doesn't matter. So I'm going to say B squared is 400 minus H squared, and then B is the square root of 400 minus H squared. And I really can't stress enough, this is not equal to 20 minus H, right? We know that this and this are not the same. Right, because it wouldn't make sense for this, you would essentially be saying B plus H equals 20. But there's no way that this length plus this length is equal to that length. It's actually something that's always true. It's called the triangle inequality, that any two sides added together are bigger than the third side. It's a very important inequality, actually. So yeah, base plus height has to be larger than the hypotenuse. If it was equal, then they would be like just a flat thing that wasn't a triangle. Anyway, back to the problem. So we're going to sub that in for the area. So now we're going to write area as a function of just one variable. You don't have to write this function notation, but I find it useful to remind myself, oh yeah, area is a function of height. And it's equal to 1/2 my, I'm going to put the height first, I guess, times the base, which is the square root of 400 minus h squared. And now we are in the lovely position of trying to find the critical values for this. It's definitely going to take more room. And one thing I would do is rewrite it so that it's not a square root, but a 1/2 power. So I'm going to say instead, the area as a function of height. Ooh. There's another way to do this problem that's just kind of tricky, but this is the way, this is the normal way of doing this problem, so this is how we should do it. But if you guys want, we could talk about another way of doing this. That's 1/2 height times 400 minus height squared to the 1/2 power. So we'll take the derivative, and yeah, we have to use the product rule. So it's going to be the derivative of this, which is 1/2 times that. 400 minus h squared to the 1/2. I don't know why I just started using brackets. Not for any good reason. Plus this 1/2 h times the derivative of this, which is going to be 1/2 times my stuff to the negative 1/2 power times the derivative of my stuff, which is negative 2h. This is looking gnarly. So this is where we do have to be able to factor. And I can factor out, I can definitely factor out a 1/2 from each of them. In fact, I can cancel a 1/2 here and a 2 here. But I can for sure factor out a 1/2. And I can also factor out a 400 minus h squared to the smaller power. Which is the negative 1/2 power. What am I left with? Well, here, I'm left with a 400 minus h squared to the positive 1 power. Now, I want you guys to think about this for a second. This power has to be 1 here because, well, you can think of dividing this out, which means I subtracted the negative 1/2 from that power, and 1/2 minus negative 1/2 is positive 1. Or you can think about it, and this is the way I really think about it. If you multiply this back through, you have to, when you multiply these together, you add those powers, and negative 1/2 plus 1 is positive 1/2. Oh yeah, that works. From here, I factored out a 1/2. Okay, took care of that. I did not factor out an h. I did factor out the 400 minus h squared to the negative 1/2, right? That's what came out in front. And I've also got an h there. So here's what I've got. I've got 1/2. I'm gonna deal with this in a second. Times 400 minus h squared. Ooh, so I made a mistake. It's a small one. It's easily fixable. Looking at this, I'm getting 400 minus h squared plus h squared, which is just gonna be 400. That's not right. This should be a critical value. There should be a minus sign, right? I lost my minus sign right there. So it actually be 400 minus 2h squared over 400 minus h squared to the positive 1/2, which is the square root of 400 minus h squared. All right. So I can divide the top by 2, or I can factor by the 2, let's say it that way. So I get 2 over 2 times 200 minus h squared over the square root of 400 minus h squared. Whew. And I want this to equal 0. Or I guess it could be undefined, but we'll talk about that. So to make this 0, the top has to be 0. So that means h has to be the square root of 200. To be undefined, the bottom would have to be 0, which means h would have to be 20. That already is terrible. The reason h can't be 20, I've got a right triangle. The height can't be the same as the hypotenuse. Not possible. At least not if you want to have a triangle. So h is the square root of 200. Is it a maximum? Well, I don't know. So I can test to see if it's a maximum. So one way to test is to say, well, this is actually where you could use the closed interval test. Say, well, I know that the smallest h could be a 0, even though that'd be kind of weird. And the biggest h could be technically, you could have a height of 20 and a base of 0, which would be dumb. But you could say, well, okay, if the height is 20, the area is going to be 0, right? Because the area as a function of height is 1/2 times 20 times 0. And if the height is 0, the area would also be 0. And so if the height is square root of 200, well, the area is definitely positive, right? 1/2 times the square root of 200 times 400 minus the square root of 200 squared. Those are both positive. So this is definitely giving us a maximum. And I guess since the question was to find the area, we should actually figure out what that is. So if I plug in the square root of 200, I get 1/2 times the square root of 200 times the square root of 400 minus 200, right? Because the square root of 200 squared is 200. So I get 1/2 times the square root of 200 times the square root of 200, which is 1/2 times 200, which is 100. I really don't actually like doing it that way. If I had to actually find the area, I probably would have said, well, I'm just going to go back and find the base. So if I plug in the height there, which is the square root of 200, 400 minus 200 is 200, so the base is also the square root of 200. So you end up getting, for this problem, if you were asked to find the dimensions, that they're both equal to the square root of 200. And then the area would be 1/2 the base times the height, which is 1/2 that times that, which is 1/2 of 200, which is 100. To me, that seems like a nicer way to do it, but take your pick. There is another way to do this problem using trig. Does anyone want to see that? It is easier. It just, you have to use trig. Okay, nobody said they wanted to hear it. That's fine. It's really fine if you don't want to see it that way. Okay, so the nice thing about using the trig is it actually really is easier. So let me just show you, it doesn't take too long. So here's my base, here's my height, and I'm going to call this angle theta here. So the area now being 1/2 base times height, well, I can write both the base and height in terms of the angle theta. I can say, hey, look, sine of theta is opposite of hypotenuse, which is h over 20. So h equals 20 sine theta. Cosine of theta is adjacent of hypotenuse. So cosine theta is b over 20. So the base is 20 cosine theta. So I can rewrite the area as a function of the angle theta. It's 1/2 base, which is 20 cosine theta, times height, which is 20 sine theta. And then I can say, okay, well, I'll do it like 20 is 400 divided by 2. So that's going to be area as a function of one variable is 200 sine theta cosine theta. So it's a really, really fast way to get your thing you want to maximize as a function of one variable. Then we take the derivative. Still have to use the product rule. It's going to be 200, let's see. Derivative sign is cosine times cosine plus sine times the derivative cosine is negative sine. Well, that equals 0. So I'm getting, let's see, 200 times cosine squared theta minus sine squared theta equals 0. So what this ends up leading me to is I want that these are to have to be equal to each other. So I need cosine squared theta to equal sine squared theta. Okay, does anybody know the angle where sine and cosine are equal to each other in either radians or degrees? Yeah, thank you. Pi over 4. Which makes sense, right? We want this angle, right? So we already saw before that the answer was that the area was maximized when the base and the height were the same. Well, that's equivalent to saying the angle is a pi over 4 or a 45-degree angle. So great, then to find the area, we jam that back in there. So plugging that in, I get 1/2 times 20 times cosine of pi over 4 is root 2 over 2 times 20 times sine of pi over 4 is also root 2 over 2. And let's cancel some stuff. I can cancel, so square root of 2 times square root of 2 is just 2. So that cancels with one of those 2's at the bottom. So I get 1/2 times 20 times 20 times 2 times 1/2, sorry, which is going to be 10 times 10, which is 100, which is the same answer we got before. So if you, this is definitely not the easiest way to think of it the first time around, but if you can see this, it becomes a lot easier to deal with, I think. Let's see, there was a couple, let's look at this, yeah. So a couple people asked about this homework problem, which is kind of wonky. I know we have very little bit of time, but this one should take just a moment to work through. So this problem says, what do we got here? A and B are positive, and we want to find the maximum value of this function, which has x to the a times 1 minus x to the b. Okay. And so your answer will have a and b in it, because it totally depends on, right, if a and b are both 1, then your answer will be different if a and b are both 2. So let's, but again, the process, if I want to maximize this, and the x is between 0 and 1. But you need to be true so that neither of these are negative. So, to maximize the thing, we take the derivative, we set it equal to 0. To maximize this, I'm going to have to take the derivative. I'm going to have to use the product rule. What's the derivative of x to a power? What's the derivative of x cubed? Oh, it's 3x squared. What's the derivative of x to the a? Oh, it's a times x to the a minus 1. Times this. And then we switch it. I get x to the a. And what's the derivative of 1 minus x to the b going to be? B going to be. It's going to be b times 1 minus x to the what power?
B minus 1.
Thank you. Times what else?
Times -1.
Right on. Yeah, exactly. There's a -1 to the chain rule there. So now the trick to this, trick being not the right word, the process here is just like any other time when you're trying to find a critical value, you really have to factor, right? Solving this equal to 0 requires as much factoring as possible. So I see an x to a power and an x to a power, and I see a 1 minus x to a power and a 1 minus x to a power. And whenever you're factoring, you can always factor out the smaller power. Which one is smaller, a minus 1 or a? Well, obviously a minus 1 is smaller. In a similar way, b minus 1 is definitely smaller than b. So I'm going to factor out x to the a minus 1 and a 1 minus x to the b minus 1. And I'm going to be left with, let's see, so from here, I'm left with the coefficient of a. I don't have any x's left because I factored out all of the x's, but I do have a 1 minus x left because I factored out a 1 minus x to the b minus 1, but I had one more 1 minus x, so I had 1 minus x to the b. Minus, so now from this piece, I have a coefficient of b. I factored out all the 1 minus x's, but I factored out x to the a minus 1, but I had x to the a, so I have an x to the 1 left over. And I'm going to set this equal to 0. Okay. So now I need to simplify this inside part. And it's not a lot of simplifying to do. Why do I feel like this looks different than when I did it before? No, I guess that seems perfectly right. So here's what I get. I have x to the a minus 1 times 1 minus x to the b minus 1 times a times 1 minus a times x minus b times x. All right, everybody. I know we're out of time, so we'll finish this up here. What's the critical value I get from this part here?
Zero.
0,
Oh, from this part.
1.
And then from here, we have to set this equal to 0. So if I set a minus ax minus bx equal to 0, I'm going to bring those over here. So a equals ax plus bx. Factor out the x. A equals x times a plus b. So x equals a over a plus b. That's my third critical value. So I've got 3 critical values on a closed interval. So I'm to figure out which one's the maximum, I'm going to plug them into the function. So again, I want to be very, very clear, and just in case you guys don't know what the problem I'm talking about is, let me share it with you so you can see it. So this is the problem I'm looking at. If a and b are positive numbers, find the maximum value of this function where x is between 0 and 1. Your answer may depend on a and b. So again, they're asking for the maximum value, right? They want to know what you get out when you plug in your critical point. So the maximum value could occur either at 0 or 1 or a over a plus b. If you plug in 0, you get 0. If you plug in 1, you get 0. If you plug in this number, are we guaranteed to get something positive? Well, is this number positive?
Yes.
Yeah.
Yes. But what about 1 minus that number? Is 1 minus that number also going to be positive? The answer is yes, and here's why. A plus b is bigger than a, so a over a plus b is smaller than 1. So 1 minus a over a plus b is still positive. So when you plug in a over a plus b, you'll get a over a plus b to the a times 1 minus a over a plus b to the b, and it will be the biggest value you can get.